So today we will be discussing Poisson's ratio. When a body is elongated by a force, simultaneous contraction of the body occurs in the direction perpendicular to the force, keeping the volume constant. That is, in this case in the figure, if we stretch the wire along its length, simultaneously there will be a lateral strain in the direction perpendicular to the applied force, which causes the wire to become thinner. In simple words, a wire on being stretched becomes longer but thinner. That is, tangential strain is always accompanied by a lateral strain. Now Poisson's ratio, denoted by sigma, is defined as the ratio of lateral strain to longitudinal strain. The lateral strain is also known as the secondary strain, and the longitudinal strain or linear strain is also known as the primary strain. The lateral strain or the secondary strain is denoted by beta, while the linear strain or longitudinal strain is denoted by alpha. We have a negative sign here because as we apply a force which causes the stretching of a wire or elongation of a wire, which causes the longitudinal strain, there will be a lateral strain which causes the thinning of the wire or the contraction of the wire. So both are in opposite sense, which is why there is a negative sign here. Now we will see the relations connecting elastic constants. The three moduli of elasticity, the Young's modulus, bulk modulus, and rigidity modulus, and the Poisson's ratio, are interrelated because a change in one dimension can result in a simultaneous change in the other dimensions as well. That is, if we stretch a wire along its length, it causes a change in its thickness, or it becomes thinner, which is why we need a relation connecting the elastic constants. So in the first case, we will be discussing the relation connecting the Young's modulus, Y, and Young's modulus Y, bulk modulus K, and Poisson's ratio sigma. For this, consider a unit cube which has side 1 unit, and we have 3 directions on each of the opposite pairs of faces, that is x direction, y direction out of the plane, and z direction in the vertical direction. So there are 3 forces in each of the directions: Tx, Ty, and Tz. These forces represent the tensile stresses on the 3 pair of faces with unit surface area respectively. They produce elongations along Tx, Ty, Tz, and contractions perpendicular to them. Suppose, and now consider this force Tx, this force causing the tensile stress in x direction, and this force causes an elongation of the cube in the x direction. But at the same time, the force Tx causes a contraction in the y direction as well as the z direction. Similarly, the force Tz causes an elongation in the z direction, but it causes a contraction along y direction as well as x direction. Now we will calculate the elongation and the elongation is given by the force times alpha. Alpha is the longitudinal strain per unit stress along the direction of the force, and beta is the lateral strain per unit stress perpendicular to the direction of the force. Then elongation produced in any edge AB will be Tx times alpha, and the contraction produced in AB due to Ty and Tz equals Ty times beta and Tz times beta respectively. That is, coming back to this figure, consider this length or this edge AB. When Tx is applied acting along x direction, it causes an elongation of edge AB. The length, that is the length of the edge AB, will increase, while the Ty and Tz forces acting along y and z direction respectively, they will cause a contraction of this edge AB, because the force along Tz will cause contraction along x and y directions. Since AB is along x direction, the length AB will be contracted. Similarly, the force Ty will cause a contraction along AB as well. Now, we know alpha is the longitudinal strain per unit stress. So dimensionally we can check this as, we can write this as strain, longitudinal strain per unit stress. Longitudinal strain is given by change in length to original length divided by unit stress. Stress is given by force upon area. So again, this length L will be 1 unit since we have considered a unit cube, and the same will be the case for the area capital A. Area will also be 1 unit since the cube is a unit cube. Now the remaining terms will be delta L upon F. Delta L upon F, and if we multiply this term alpha with F, where F is the force along any particular direction, the F cancels in the numerator and denominator. The only term remaining will be delta L, and this delta L represents the elongation or change in length. So force along a particular direction times alpha gives the elongation. So similarly, force times beta gives the compression as well, contraction as well. Now again, look at this edge AB. As these forces are acting in x, y, z directions, I've already said that the force Tx causes the elongation of AB, and the forces Tz and Ty causes the contraction of AB. So the original length of AB was 1 unit, and due to elongation, we have already understood that the elongation will be the force times alpha, that is Tx times alpha. So since Tx is the force causing the elongation will be Tx times alpha due to the reason we have discussed in here. So Tx times alpha gives the elongation, and the contractions is given by Tz times beta and Ty times beta. So the length of AB will become the original length, which is 1 unit, plus the elongation Tx alpha, and the contraction. Contraction will be given in minus sign because they causes the length of the AB to decrease, which is why we have subtracted this lengths. Now similarly, the length of edge BG and BC can also be written, and the volume can be calculated by just multiplying these 3 sides. So this will be the volume of the new cube, and after binomially expanding this and neglecting the products of alpha and beta and their squares. Since alpha and beta are very small quantities, their squares or product values will be very small, so all those terms can be neglected, and taking the Tx, Ty and Tz to be equal, that is the force in xyz direction to be equal, say T, then we will be obtaining the final result as this: 1 plus 3T times alpha minus 2 beta. So this will be the volume of the new cube. The increase in volume can be calculated by subtracting the original volume from the new volume. So the new volume is 1 plus 3T times alpha minus 2 beta, and subtracting the original volume, which is 1 unit. So 1 cancels, and finally the change or the increase in volume will be 3T times alpha minus 2 beta. Now the volume strain can be calculated by change in volume upon original volume. Change in volume was 3T times alpha minus 2 beta, which we have seen, and the original volume was 1 unit. Now the bulk modulus will be stress upon volume strain. The stress is the force upon area. Force is T here, area is 1 unit, so it will be T by 1, which is T itself. The volume strain is 3T times alpha minus 2 beta, which is substituted here. Now the bulk modulus can be obtained from here, since T cancels. So again, now in this case we have calculated the bulk modulus for the case in which we have applied, the force is being applied causes the elongation. The force applied causes the elongation of the cube. We can also consider the case when the force applied causes the compression of the cube. In that case we calculate the decrease in volume, so which will be obtained, which we will get the same value as this. So finally the bulk modulus will be obtained as 1 upon 3 times alpha minus 2 beta. And now taking alpha common from here, we obtain 3 alpha times 1 minus 2 beta upon alpha. So beta upon alpha is nothing but the Poisson's ratio, and alpha can be taken to numerator, which will be 1 upon alpha. And we know that alpha is longitudinal strain per unit stress, whose reciprocal will be stress upon strain, which is nothing but the Young's modulus itself. So substituting the value Young's modulus here, so we will obtain the relation connecting Young's modulus, bulk modulus, and Poisson's ratio.